Started. Yeah, we're talking about the bell work. Remember we said what might a loud sound look like and what might a quiet sound look like. And remember guys, a loud sound is one that has high amplitude, and a quiet sound is one that has low amplitude. Okay, and so here we have two different sound waves. Okay, the top one would have low amplitude, and the bottom one would have high amplitude. Okay, so which one of those would be louder? Bottom. Okay.
How do I draw that? A bunch of dots?
I don't know. Just put a whole bunch of dots. You know, have a good time. I gave you plenty of time to draw lots of dots.
I didn't know
Huh? Do I have y'all nervous or something?
Yeah,
Okay. I mean, I don't have anything hidden that I. There's not like a monster inside waiting to come out. What now? Okay. Question. We said the bottom sound wave was louder. Does the bottom sound wave sound any different other than being louder?
No.
How can you tell? The compressions hit at the same time, right? So in other words, this sounds the same. The bottom one's just louder. Okay, do they travel at different speeds? No, because they're in the same medium. All right, so today we're going to be talking about one more aspect of sound waves. And I'm kind of going through it. We already talked about all this. I just wanted to go back to that picture. Okay, and this is going to govern how they sound different. Yes. Can we do something about it? Okay, I could do it. You want me to turn it off?
No.
Oh, I thought you will. You just said do something about it. I did something. Ah!
You finna snap on that. Just put the desk and watch it.
I guess. So, the difference between and okay, is what?
Louder. Closer together.
What wave characteristic?
Louder. More amplitude.
The amplitude, right? Okay, it's louder. Okay? So the only difference between those two, more energy, louder. Okay, and then I'm trying to get y'all to start breaking away from the idea that sound is sound and start to cling more onto the idea that sound is a compressional wave that we can perceive. Okay? So when we're hearing sound, we're just perceiving a compressional wave. Okay, in the same way that you feel touch. I mean, sometimes it's like sometimes you might get touched and it feels like a tickle, and sometimes you might get touched and it feel like pain. And I mean, those are all just a force, right? You're perceiving a force. Okay. Well, with sound, that's a way that we're perceiving a compressional wave. Okay. And so another aspect of a sound wave that we are capable of perceiving is the pitch. Okay, and the pitch is going to be the difference between and same volume. Okay, how do they sound different? And to me, it's kind of hard to describe that. High, it sounds high or low. I don't know what it means to sound high. I mean, when you really think about it, that's kind of hard to describe, isn't it? It sounds high. What does it mean to sound high? I mean, that's. I mean, other than like, like what is it? That's kind of hard to describe. When I actually ask you to put it into words, the only thing I can think of is pitch. They just sound different to me. One sounds squirrelier and one sounds burlier. Anyway, okay, that pitch, guys, is going to be related to the frequency of the sound wave. Okay, the frequency. And remember, guys, what is frequency? This is going to be in the test coming up. It is kind of related to the speed.
How many times a certain point in a compression wave?
Okay, it's how many times the wavelength comes per second, right? Okay, so that's the frequency. Okay, so something that's high pitched means that a lot are going to come per second, and something that's low pitched means not much is going to come per second. Well, it's still going to be a lot, but not comparatively. Okay, so the frequency is the measure of how many wavelengths pass a fixed point every second. Okay, for what kind of wave is a sound wave? Compressional. Okay, so for a compressional wave, our wavelength is going to be, or our frequency is going to be the number of compressions that pass every second. Okay, what I mean by pass is if I'm like at your ear, okay, or if I'm your tympanic membrane, then the frequency would tell me how many compressions hit my tympanic membrane every second. Okay, and how many rarefactions hit that tympanic membrane every second. And if it's a lot, then it's a lot. And if it's a lot, it sounds higher. If it's a lot, does it sound louder? No. What makes it sound louder? So amplitude, in other words, if they hit really hard. Okay, so if they hit your tympanic membrane really hard, it sounds loud. And if they don't hit so hard, it doesn't sound so loud. Okay. What now? If somebody hits you? Like a person? Yeah, absolutely. Okay, frequency, guys. We're going to be measuring frequency in hertz. Hertz, Hz. Okay, and that number, that hertz tells me how many per second. Okay, so when I have a sound wave with high frequency, okay, then many compressions hit your eardrum every second. And if I have a sound wave with low frequency, then not so many every second. Okay, guys, if you remember, and I've already played this before, but I just wanted to remind you. Okay, this is a frequency of 1,000 hertz. Okay, so if it's 1,000 hertz, then that means every second, 1,000, what? 1,000 waves hit your eardrum, right? Okay. So that is a frequency of 1,000 hertz. Okay, if I double that to 2,000 hertz, it's going to go up. Specifically, every time you double the frequency, it goes up an octave. Okay, so that's what an octave is. Okay, so that da da. You know that is an octave. Okay, if I'm doing a scale, that'd be da 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 da. Okay, so if you're up an octave, octave. So that would be you go up octaves by doubling frequency. Right now at 2,000 hertz, that speaker is moving in and out 2,000 times per second. Okay, so every second, 2,000 times. Your ear just does whatever the speaker does. Okay, so if the speaker is doing 2,000 times per second, then that tells me that my ear is doing 2,000 times per second. Okay, so if the speaker is I whip my hair back and forth, then your ear is I whip my hair back and forth. Okay, yeah.
Does the same thing. Do those wavelengths or whatever make you go to sleep?
I've heard about certain things like that. I don't know if there's any credibility to that. No. Okay, so does that make sense, guys, of why our hearing is limited? Okay, I can't hear above 20,000 hertz. Why do you think that's the case? Your eardrum just can't move that fast. Okay, it's just limited in how. Does that mean that there's not possible to have a sound wave above that frequency? No, I mean that speaker can move faster than that, but that speaker is not made of a tiny 0.1 millimeter thin membrane that's vibrating. Okay, so it's capable of going higher than that. Yeah. Do you have a question? Oh, I thought I saw a hand over there. Okay. Maybe I was just hoping. Questions. I saw that. But keeping in mind, guys, okay, our brain is just interpreting that. Okay, so really, in terms of a sound wave, a high-pitched sound wave wouldn't look so much different than a low-pitched sound wave. Okay, I mean, sure, the compressions would be closer together. Okay, that would be the frequency; they'd be closer together, but not much difference. Okay, the only difference is that we're perceiving it as being higher. Okay, in the same way that I might perceive that light to be blue, is that light actually blue? No, it's just a wavelength of blue. Okay.
How do we know this thing?
Huh?
How do we know this thing?
Well, there's really no such thing as blue. It's just that is the wavelength that corresponds. We say, that looks blue to me, and our eyes are interpreting that as blue. It's just a different wavelength of light.
Well, we were taught blue is red, so let's check this red.
Yeah, that thought has occurred to me several times that it could be possible that when I'm looking at that blue, you could be looking at that blue and actually seeing what I would call red, but you were just taught that it's entirely possible. Yeah, and it's just your brain. And to be frank, the same thing could be true with sound. Really, you could be hearing sound really differently than I am because it's just your brain interpreting vibrations. Now, most likely, we're hearing similar things. That's what I would speculate. But if you hear a sound differently, and they say, "Okay, emulate that sound," well, you're going to emulate the sound the same way you hear it, and so it's going to make the same sound that I would hear.
But if you heard a cow sound, you start making chicken noises.
Yeah, but whatever compressions you interpreted, you would make those same compressions. It's just like copying a tape, or that maybe not the same, but you'd make similar as you could. Anyway, let's move on. All right, so ultrasonic, guys. Anything above 20,000 hertz, we're going to call ultrasonic. Ultra means higher. Okay. Okay, or the best, the highest. Okay, so ultrasonic, anything above 20,000 hertz.
Any frequency?
Any frequency, yeah. Okay, so to kind of demonstrate ultrasonic, if we're listening to it. Okay, that's 2,000 hertz, 6,000 hertz, 16,000 hertz, 19,000 hertz, 20,000 hertz. It just gets higher until you can't hear it. Okay, so that's ultrasonic. Okay? Why not? Yeah. Okay, so fundamentally, guys, is there any difference between an ultrasonic sound and a not ultrasonic sound in terms of the way they're produced or the way they're perceived? No difference. Okay, the only difference is that we cannot hear it. This is why I'm trying to get us to move away from sound as something you hear. Okay, sound is a compressional wave, and we perceive it. Yes. Somebody have a question?
Oh, if you have those sound isolated earbuds and you play that, would you still be able to hear it?
Not if you canceled it out.
I'm talking about cancel out other sounds.
Cancel out other sound.
Like if I had that same
No.
thing.
No, because your ears cannot detect sound waves that high. It's almost kind of like, you know how like on your computer you could have iTunes playing and something else playing at the same time, like two different sounds, and you could take the iTunes and inside the iTunes you could turn down that volume and have the other one still playing. Okay. Well, I mean, if it, for us, for humans, it's almost like one of those. You can slide the volume back and forth and it doesn't matter because we can't pick it up. So we have no perception of that. So even if you cancel out all the rest of the noises, well, you still can't perceive that sound. So that makes sense. Okay. And even though we can't hear ultrasonic, guys, we do use it for a lot of things. You'll hear about ultrasounds a lot. Like if you, sometimes if they want to look and see what's going on with some of your organs, or if if a woman is pregnant and she's going to the doctor to get checked up, they'll do an ultrasound. Okay, that's essentially just blasting sound waves at your body. Okay, and you can't hear it because it's higher, but it's really just a sound wave, right? Blasting sound waves at your body, and then using those to detect things. Okay, we use the exact same principle with sonar. Okay, sonar can be used to detect how far away things are. Typically, they'll send like a little ping. In subway movies, they like to make it really dramatic, and you hear boom, and it makes this sound. But that we use ultrasound. I mean, you're not actually ultrasonic. You're not actually going to hear it. Some animals use ultrasound. Dolphins, bats. Okay, but actually dolphins, it's not ultrasound. They use frequencies that we can hear.
Can dogs hear ultrasonic?
Some. They can hear higher than we can. They can probably hear into the ultrasound range, but I mean, ultrasound it's kind of like it's like there's a volume on an intensely loud stereo speaker system, and at 20, we start to call it something else, and from then on, it's that. Well, here from then on, it's that. I mean, dogs can hear a little bit of it, but they can't hear everything. Be good? Alright, the next concept, guys, before we even get there, I'm just gonna demonstrate it with a sound, and you're gonna know exactly what I'm talking about. Okay? You ready? Yeah.
Airplane. Car.
It's not sure.
Car.
Ew.
A bee.
Race ball.
Okay. There's
Move so it goes.
there's a lot of cases where we hear that, right? Like a race car going by, a plane going by, a bee. Sometimes if they go by your ear really quick,
A bullet flying by your ear.
a bullet flying by your ear. Hopefully that doesn't happen very often. A NASCAR. Okay, there's a lot of times we hear that. And every time we're hearing that, guys, there's always something happening. Something is always in motion. Okay, that is called the Doppler effect. Okay, and the Doppler effect is an apparent change in frequency due to a moving wave source, or due to a moving sound wave. The sound waves always move. Due to moving things. Let's say moving things. Gladys, did you just tell me to check myself? I thought. Uh-oh. No. No, stop that. Alright. I'm sorry, guys. I forgot to open up the document camera. Alright, so Doppler effect, guys. Apparent change in the pitch of a sound due to motion. Okay? The Doppler effect occurs anytime the source of the sound and the listener of the sound are moving relative to each other. Let's break that down. It occurs when they're moving relative to each other. Okay, does that mean it only occurs? Does that mean it can't occur if they're I don't know how to phrase this question. I know the question is just ready to, it's trying to burst its way out, and I can't get it out. Just forget it. Just forget it.
Okay.
But,
English is not gonna be on the test, right?
No, it'll be on the test.
You should have done it.
All right. Let me just explain that. If two objects are moving relative to each other, that means their distance is changing. The distance between them are changing. Okay, so in other words, both objects could be in motion and have no Doppler effect. And if both objects are in motion and there's no Doppler effect, okay, then that means that they're not changing distance from each other. So, for example, if you're running circles around me, if you're just going around me in a circle, the distance between us is not changing. So there's going to be no Doppler effect there, even though you're moving and I'm not. Okay. Now you told me you were saying NASCAR. Okay, NASCAR, I'm outside of the loop. I mean, if I'm in the inside of the loop and you're going in a circle, I don't hear anything. Okay? But NASCAR, they're going in a circle or an oval. What? All this NASCAR talk is making me bitter. Both were moving. You can. Okay. So let me explain this, and I'm gonna draw it because I want to draw. That man what? All right. So let's say I have a car. That's my best car drawing ever.
It's a car.
And there's a rainbow. No, that's sound waves. Okay, so that's a car. It's making some sound waves. You see those sound waves traveling out, right? Okay, they're moving out. Okay. Okay, so which one of these sound waves was made first? Sound wave 1 or sound wave 2? Sound wave 1 was made first because it's farther out, right? So it's moved farther out. Let's say there's a person right here at sound wave 1, and there's a person right here at sound wave at that one. Y'all agree they hear it at the same time, right? Huh? Yeah, this is the same sound wave. They hear it at the same time because they're the same distance, right? All right. So right now that we're going to say that this object is stationary. It's making a sound. Okay, those sound waves are just moving out. They've been moving out in circles, right? Let's say that object is not stationary. However, let's say it's going to be moving with the arrow. Okay, so we said that this sound wave 1 got produced first. Sound wave 2 got produced second, right? So if this object is moving this way, let's make this 2 and make this one 3. Sorry. Okay, so it's already produced sound wave 1, right? So now it's moving this way. So instead of being right here, since it's moved forward, okay, sound wave 1 is produced sound wave 1, it's moved out, it's moved forward now. So let's say it's right here. Y'all agree that's possible? It made a sound, that sound moves out, now it's moved forward? Y'all agree that's possible? Okay? If it's moving forward. So now it produces sound wave, it produces this sound wave. Alright, let's say it moves forward again. Maybe it's going to be here now. It's going to produce the next sound wave. Do y'all see what's happening?
It's leaving sound wave.
It's what now?
Leaving sound wave.
It's making the same sound waves. You see they're the same size sound waves. But on one side they are closer, and on one side they're farther apart. If I have waves that are close, that means I have a small wavelength. So on this side I have a small wavelength. And on this side I have a large wavelength. Right? Using the formula V equals F lambda, if I have a small wavelength, what is my frequency? Starts with an L. It starts with L, ends with large. Large, okay? Okay, so, and this side, I'm going to end up with a large frequency. In other words, it's going to sound like, ah! Okay, and on this side, I'm going to end up with a small frequency, so it's going to sound like, ah. Okay, so do y'all see when this thing passes, I get a ew. Huh? You say yes or no? Look. Okay, let's get back. Did y'all agree with this picture? Did this picture float with everybody? No, this one right here. A car makes a sound wave. The sound wave moves out. The car moves forward. It makes another sound wave. Okay. Can do. Ask and you shall receive. Let's see. Oh, this is a good one. Oh, this is a good one right here. Alright. Look here. This motorcycle is moving in this direction. So even though those sound waves are moving forward, the next sound wave it makes is going to be closer to the forward sound waves because it's moving in that direction. Let's think about it this way. No, that's too complicated.
So the man sitting there is like hearing it louder than the girl sitting behind him.
He's not hearing it louder. He's hearing it higher. You see, because... No. Look. Right here. You see how the waves are close together? That means it's a small wavelength. Small wavelength means high frequency. Okay, so up here I'm hearing... Okay, and then back here in the back I have big space. So that means low frequency. So I'm hearing... So I hear... Meow. Do y'all need a video?
I'm not understanding the concept.
Alright, hey, Gladys. Gladys, I'm gonna get you a video. It's gonna be okay.
I thought a child me interested.
I can't promise that this video is gonna be any good. I haven't seen it. But this is gonna be a good video. I can just tell. Oh, this is good. This is good right here. This is good. Yeah, man. Somebody hit the lights. Somebody hit the lights. Oh, I want to see an animation. Huh? What does what mean? It's not slowing down. The frequency is changing. I want a video. Here, give me the video. Oh, here we go. I hadn't seen this, so I don't know if it's any good or not. Alright, I'm hoping it's going to show it moving instead of all these texts. Come on. Alright, so if it's just sitting still, it's creating sound waves that are all the same. You see how it's the same space in every direction. But if that orb moves upward, you see how it'd be closer to one of the sound waves than it is to the other one? And if it made another sound wave, it would be closer. I'm hoping it'll just show us instead of doing all this talking. Oh, I'm glad You see that? How since it's moving toward the front of the sound wave, it's getting compressed in the front, it's getting stretched in the back. So that's high frequency in the front, low frequency in the back. Good? Okay.
Let's go.
No.
Me and everybody.
We have something else we need to talk about. Okay, so let's say that you're standing right here. You're in a box. You're a box. And you have a train horn beside you. And that train horn is at 500 hertz. Okay, so you hear a train horn at 500 hertz. You know there's an identical train horn. It's off in the distance. It's moving somewhere. I don't know where it's moving. But you hear its waves as 400 hertz. Is that train moving towards you or away from you? Okay, first of all, does it sound higher or lower? Sounds lower. So is it moving towards you or away from you? It's moving away from you. Okay? So this one would be sounding like and this one would be sounding like and so you would know that this was moving away. Okay, and I will. Okay? So the rule, if the two objects are moving toward each other, it sounds higher, and if they're moving away from each other, it sounds lower. Okay? The Doppler effect also happens when the source is stationary and the listener is moving. Okay, so for example, let's say I have the ground, and we have a weather siren. Okay, and that weather siren's making some sound waves. Okay? So, if you're just sitting still, you'd hear the exact same sound over here that you heard over here. Okay, however, if you were driving toward that weather siren, you're going to hear ew. Okay? So if you're in motion, you'll also detect the Doppler effect, even if the source is stationary. So let's look at how that happens. If you're over here and you're moving in this direction, you're moving into the sound waves. Okay, think of it this way. If you're in the beach, you know, the waves are coming towards you, and you leave and you head toward the source of the waves, do you agree that you're going to hit a wave more frequently because you're heading toward the waves? Right? So since you're heading toward the waves, you're going to have a higher frequency because you're going to hit them more frequently. But when you get over here, you're heading away from the source of the waves. So you're going to end up with a lower frequency.
What is the person like on the motorcycle in the car here?
What now?
What is the person on the motorcycle or on the car in the car here?
What do they hear? Ew. Who's on what? I'm confused. A person? Who is it?
It's you.
It's me. Whoever. Whomever. Was I done talking? Let me think.
Yeah, you're done.
Alright. But notice, guys, the rule here, they're moving toward each other, and so it sounded higher. Here they're moving away from each other, it sounds lower. Okay? So we good on pitch and Doppler effect, guys?
I hope so.
Alright.
Well,